All right, so what we're going to look at now is one of the most powerful applications of eigenvectors and eigenvalues that we have, and also one of the primary reasons why we're bringing up eigenvalues and eigenvectors inside of this course at all. Other than the fact that they actually are really important, you're going to see them all over the place, right? But from a perspective of like what we're going to be doing in just a little bit, diagonalization is it. This is what we really want to, like, what we've kind of been building up to, and that's going to, like, really help us to move forward and work with especially systems of differential equations. So we'll see this a lot inside of solving systems of differential equations. So inside of diagonalization, we want to start out with this idea of what is a similar matrix. So two matrices A and B are similar if there exists an invertible matrix S such that A equals S inverse at BS. So basically what we're going to be able to do is we've got this matrix S, and if we right multiply B by S and then left multiply S inverse by BS, we end up getting A. All right? And if you kind of think about this, like what this means is it means that A and B are in many ways very, very much the same. Okay? In terms of, like, say, for example, like row reduction. All right, so now what we're going to look at is something called the diagonalization theorem, and this is the big theorem from this particular section. So an n by n matrix is similar to a diagonal matrix D if and only if A is non-defective. If V1 through Vn are the eigenvectors of n with associated eigenvalues of lambda 1 through lambda n, then S is going to equal V1, V2, V3, all the way through Vn. So the column vectors of S are going to be made up of the eigenvectors in order, by the way. We're going to do this, you're going to see it's going to be in order, and S inverse AS will equal the diagonal of lambda 1, lambda 2, all the way through lambda n. All right, so we're going to do a little thumbnail sketch of this proof to see what's happening. Let's assume that A is non-defective, okay? And so A is non-defective and so is similar to a diagonal matrix. So we're going to prove here, we're going to let A be non-defective. So that means that we get, so A is similar to a diagonal matrix. Specifically, this diagonal matrix D, which is lambda 1, lambda 2 through lambda n, all right? We're going to let D be the diagonal matrix and let S equal V1, V2. So it's basically the matrix as we set it up through Vn, where V1 through Vn are the eigenvectors of S. Excuse me, the eigenvectors of A. Okay, so that kind of gives us our setup. We're going to set up S this way. Okay, V1 through Vn, those are our vectors. A is non-defective, so that actually tells me that I have n vectors. All right, and actually I should say let be a non-defective n by n matrix. So I've got n of them. So now I'm going to say that A equals S inverse ds. Okay. And so consequently what that means is, and that's our diagonal, that means that if I multiply on both sides S inverse ds equals, so A is a diagonal, A is similar to a diagonal matrix. So what that means is that S inverse AS is going to equal D. All right, that's our definition of similarity to that diagonal matrix D. So AS is going to equal D, or is going to equal SD. Okay, AS will end up equaling SD because we just multiplying, we're going to right multiply by S on both sides. Now AS, A is going to be multiplied by V1, V2, all the way up through Vn. Okay? All right. And so what you'll want to notice is that that multiplication basically is going to take the matrix A times V1. That's going to be our first vector. here. So that's AV1, then AV2, all the way up through AVN. All right, and you may have noticed that as you do matrix multiplication, that's what happens. Now, AV1 equals lambda V1 as V1 is an eigenvector. And so lambda 1, we'll call that lambda 1, is our associated eigenvalue. This is true for all VI. For every one of our vectors, that's going to be true. So every time I do it, AV2 equals lambda V2. AVN equals lambda Vn. So this matrix here, right, AS is going to then equal lambda V1, lambda 1 V1, lambda 2 V2, right? Because those are what they're equal to. All the way out to, lambda n Vn. Now, you'll have to go kind of see how this works. You might want to do the multiplication, see what's happening here. But basically what this means then is that means that we can take this matrix, V1, V2, all the way up through Vn, and we're going to just multiply it by that diagonal matrix. We call it diag of lambda 1, lambda 2, all the way up through lambda n. And that's because basically what we're going to do in order to do this multiplication is essentially going to be that matrix S, which is what this is, that's S, times, and then we're going to multiply, we've got the identity, well, not really the identity, we're going to just have this matrix here. The way that the multiplication works is this is going to be lambda 1, lambda 2, all the way down through the diagonal, okay? And that multiplication, these two multiplications end up giving us the same thing, okay? It's an operation. I don't know, we proved it a while ago, but that operation, that's basically how it works. If you have a set of vectors being multiplied by constants, okay, what you can do is you can pull out the constants and multiply it by the identity, right? And you get a diagonal matrix. You basically will get a diagonal matrix with all the constants along the diagonal, right? So that's basically what happens. So if we look at this, right, what that means is that this is then S times, and the diagonal matrix that our similar matrices, or that our matrix A is, that our matrix A is similar to, is in fact the one that has the diagonals, that has the eigenvalues on the diagonals. The sheer number of syllables in doing that, and I was speaking English for most of the way. All right, so basically the idea is this, is that we've got a matrix A, okay, and if we know its eigenvectors, it in fact is non-defective, so we know its eigenvectors, okay, and we have all of its eigenvalues, right, and it has enough eigenvectors, then what we can do is we can actually, basically break down our matrix A into the inverse, or into the matrix of its eigenvectors times the diagonal matrix times the inverse of its eigenvectors. And that's what we can break down A into. You'll see some different ways to write that. We'll talk about those as well. But for our purposes, that's really what this is saying. And notice a couple things is that A has to be non-defective because we need n, right? N linearly independent eigenvectors in order to actually create a matrix that we can multiply by, right? Otherwise, we won't have a matrix we can multiply by. In fact, we won't have one that's invertible, and that causes all sorts of problems too, okay? So let's take a look at an example of how this kind of works. It might actually help us out a bit. All right, so now let's go through and let's diagonalize 3, -2, -2, -3, -2, -6, 3, 6, and 10. All right, so we go in, we you throw it into your calculator so that you can figure all this stuff out, right? And you get lambda 1 equals 4. All right, and so that we get that V1 is going to equal -2, 0, 1, and V2 equals -2, 1, 0. And then lambda 2 is going to equal 3, and v3 equals 1, 3, negative 3. So what we want to notice is we want to look here and we want to say, okay, well, if I, just as a kind of refresher, the algebraic multiplicity for lambda 1 has got to be 2. Okay, it's got to be 2, and actually you could see that instead of its characteristic polynomial was negative lambda minus 4 squared and lambda minus 3. But it had to be at least 2, right? So m1 equals 2, n1 equals 2, because that's the geometric multiplicity. Those two are equal. And then lambda 2 equals 3, okay? And so that means that m2 equals 1 and n2 equals 1. Your algebraic and geometric multiplicities equal to 1. They're all equal, so consequently this matrix is non-defective. You could also, by the way, see that we have an eigenbasis, right? We have 1, 2, 3 eigenvectors that we found, and this matrix is in C3, or actually the vectors in the matrix are in C3, so consequently we form a basis for C3, so A is non-defective. We can diagonalize. If A is defective, you cannot diagonalize. If A is defective, you cannot diagonalize, so we need to make sure that A is non-defective in order to diagonalize it. And now what I need to do is I need to actually construct the diagonalization. So if you remember, A is going to equal S inverse ds. Oh, excuse me, it's going to be SDS inverse, excuse me, SDS inverse. So what we're going to see then is that S is the matrix of the eigenvectors, and I'll set them up as negative 2, 0, 1, negative 2, 1, 0. So basically I'm just going to place my eigenvectors, and 1, 3, negative 3. Now, really important, something that actually kind of gets missed a little bit whenever we diagonalize, there's S. My matrix D has to have the eigenvalues in the same location as their respective eigenvectors. So notice that the first two columns go with lambda 1 equals 4. So we need to actually make sure that the first two columns in our diagonal matrix are the 4s, and then the third column, which has our third vector, is a 3. So this becomes 4, 0, 0, 0, 4, 0, 0, 0, 3. Done. So now I just need to find S inverse. So I'll plug that into my calculator. So when I plug that into my calculator, I get that S inverse is equal to 1/3, 1/6, 1/6, 1/4, 3/4, 1/2, negative 1/4, negative 1/2, negative 1/4. So A, my matrix, is going to equal, I've got S, so it's going to be negative 2, 1, 0, 1, 3, 1, 0, negative 3, then 4, 0, 0, 0, 4, 0, 0, 0, 3, and then finally multiplied by 1/3, 1/6, 1/6, 1/4, 3/4, 1/2, negative 1/4, negative 1/2, negative 1/4. And that is called my diagonalization. There is the diagonalization of A. All right? Let's take a look at another example. All right, so let's say we want to diagonalize this. We've got A equals negative 1, 1, 0, 0, 0, negative 1, 0, 0, 0, 0, negative 1, 0, 0, 0, 0, 1. Okay? So when we go through, we find our characteristic polynomial. We get I get lambda equals negative 1. Okay? And that ended up having an algebraic multiplicity m1 equal to 3. And it had a v1 equal to 1, 0, 0, 0. And a v2 equal to 0, 0, 1, 0. Then lambda 2 was equal to 1, and it had an algebraic multiplicity of 1, and it had then v3 is equal to 0, 0, 0, 1. And that's it, right? We got 3 plus 1, Those are algebraic multiplicities. They're going to equal n, which is 4. So that's all we got. That's all we got when we actually went out and found it. Well, here's the problem. A is defective. A cannot be diagonalized. So we're done. There is no diagonalization for this because A is defective. Okay? A cannot be diagonalized. And we're done. All right? So let's consider this matrix. We've got A equal to 3, -2, 3, -2, -2, 3, -2, 3, 3, -2, 3, -2, and -2, 3, -2, 3. When we go in here and we actually diagonalize it, we get that we first got lambda 1 equals 0. Okay, or excuse me, we find our eigenvectors. Lambda 1 equals 0, and we get v1 equal to -1, 0, 1, 0, and v2 equal to 0, -1, 0, 1. Okay? Notice that our algebraic multiplicity m1 is equal to 2. Then I have lambda 2. Lambda 2 is going to be equal to 2, and it's got an associated eigenvector of v4 equal to, or v3, excuse me, v3 equal to 1, 1, 1, 1. It also has an algebraic multiplicity m2 equal to 1. And then we have lambda 3. Lambda 3 is going to equal 10. And it has an associated eigenvector of v4 equal to -1, 1, -1, 1. So I look here and I notice, I have an eigenbasis. 1, 2, 3, 4 eigenvectors for my C4, for my vectors in C4. So I should be able to, I can generate an eigenbasis. Okay, so hence A is non-defective. This will allow me to diagonalize it. If A was defective, we would not be able to diagonalize. So I go in here now and I'm going to say, okay, A equals, remember it's going to be S ds inverse. We're going to let S be the eigenvectors, and I'm just going to put them all in order. The order that I have them here, -1, 0, 1, 0, 0, -1, 0, 1, -1, 1, -1, 1, and then 1, 1, 1, 1. We'll multiply that by the associated diagonal matrix. Remember, you've got to have, along the diagonal, we have to have, if column 1 and column 2 are go along with lambda 1 equals 0, then we have to have zeros in the diagonal there too. And then I'll have lambda 3 is going to, lambda 2 is 2, so that goes along with, oh wait, actually the way that I wrote it, yeah. I got lambda 3 equals 10, so I got this, -1, 1, -1, 1. So that means that I've got to have 10 in column 3, and then I can have 2 in column 4. So the order that I actually put the eigenvectors into is not important. What's important is that where we put our eigenvalues has to correspond with their eigenvectors. So like, for example, in this case, I put v4 into the third column. That means that I had to put 10 into the third column in D. All right, so that's really important. Does it matter what order you put those eigenvalues into? No, as long as it matches up with where their associated eigenvectors are in S. And then I'm going to have S inverse. So what we're going to do basically is we'll go in and we'll find the inverse. And so my inverse matrix here is going to be -1/2, 0, 1/2, 0, 0, -1/2, 0, 1/2, -1/4, 1/4, -1/4, 1/4, 1/4, 1/4, 1/4, 1/4. And that is our diagonalization. So it is S ds inverse. Let's go in, let's actually kind of review just some important things. Right? 1, A is similar to, and this is the diagonal, diag of lambda 1, lambda 2, all the way up through lambda n, where lambda n, where each lambda I are the eigenvectors or the eigenvalues of A if A is non-defective. So if A is non-defective, it's going to be similar to a diagonal matrix made up of, along the diagonals of its eigenvalues. 2, okay, if A is non-defective, A equals SDS inverse. By the way, you may see this in other places as PDP inverse. I learned PDP inverse when I was growing up in my math world. And it's just P is just the matrix of the eigenvectors as well. You may see that around. And then 3, okay, that's only if A is non-defective. If A is defective, A defective implies A is not diagonalizable. And then 3, okay, we must place the eigenvalues in the same column, in the same columns as their associated eigenvectors. And that is the third part there. Okay, so just some things to remember as you're going through and working with diagonal matrices. All right, so use your technology in order to go find those eigenvectors. Make sure you may have to use that characteristic polynomial function to figure out whether or not the matrix is defective or not. But if it's non-defective, you can diagonalize.